So the title is indeed scaling in tensor networks in 1D and 2D. So I think this is the higher dimensional tensor network kind of a session. So I will include a little bit of 2D in my talk, but more generally the outline is the following. So I think we will mostly work with kind of infinite system matrix product states and also infinite system PEPs. So I'm quite a fan of these ideas which have been introduced by Guiffre and collaborators over the years. And I think it's a very interesting paradigm to do many-body physics. And I'm also passionate about understanding conformal field theories in various circumstances. And it actually turns out that MPS, particularly IMPS, and also IPEPs are a good framework actually to investigate this challenging system, even though kind of, at least in 1D, they violate the area law mildly, so you might think this is a hard case, but I hope to show you that you can indeed get very accurate results, at least for the Ising model, but also still decently accurate results beyond the Ising model as well. And so there are three parts I would like to present you. They're not closely connected, so if I run over time, I can stop also a bit earlier. But I would like to start first with a more recent work, which we just put on the archive, where we were intrigued, like hopefully many others, to understand what is the spectrum of the transfer matrix if you're in the finite entanglement scaling regime of IMPS. And we made an interesting observation, which turns out to be quite a powerful practical value. So this is to extract the speed of light from IMPS simulation. So that's one project. And then the other one is kind of work we're about to wrap up with Alex Eberharter. So that's actually kind of trying to overcome some kind of challenges in the finite entanglement scaling, which have a good precision, but it seems to be difficult to systematically improve it. And so we were actually playing by adding a relevant perturbation to the CFT, therefore gapping out the system and inducing a physically finite correlation length. And then one can actually analyze MPS data with high accuracy as a function of this perturbation, and that turns out to be quite an interesting handle also on critical systems in some cases. And then in the end, I do justice to the higher dimensional part, and so that's work which is a bit older, but we have been trying to understand how one could generalize ideas which are called finite entanglement scaling in 1+1D, but what is kind of a similar approach for IPEP simulation. And so we and Philippe Corba and Luca Tagliacozzo worked in parallel on the same problem, and so we came up with this finite correlation length scaling approach. Okay, so that's kind of the menu for today. Let's start with the first part. And so this is extracting the speed of light from IMPS. And so let's discuss what actually the first question was. So here I present you the motivation from the point of view that, like, historically, I think if you look in the old literature on DMRG at the time, and also analyzing critical systems, you see in the early days, say in the 90s, when MPS DMRG at the time was around, people were already then interested to measure central charge, but at the time it was not understood that the entanglement entropy was governed by the central charge primarily. And so people actually used the Casimir effect. You see that's a famous result from conformal field theory. It's that kind of the ground state energy. It's extensive and it has an offset, but then there's also some correction to kind of which is governed by both the central charge and the velocity. So you know that if you work in a Hamiltonian formulation of conformal field theory, then actually the space and time are, have the same power laws, but there's a prefactor which relates the two directions. That's actually the speed of light or the speed of sound. And so, in those early works, you actually needed to know both kind of measure ground state energies, but you also needed to have an estimate for the sound velocity or the speed of light to actually infer the central charge. So before using the entanglement entropy, you actually had to do both. And actually turned out it was really difficult to get the high precision on the speed of sound, and also it relied on kind of knowledge of the conformal field theory in the first place to actually estimate what the speed of sound was. Then in recent years, there has been some work by the Ghent group, but also Lawrence and I guess Yuto and Frank and others, basically constructing excitations and then investigating the low momentum behavior of excitations. One can also infer the speed of sound to some extent. And so something I would like to show you now is that there was also an approach by Natalia Rzepiga and Frederick Mila, where they made an interesting observation about the spectrum of the local Hamiltonian in a DMRG. And that's actually a second motivation, I will come to that, is actually to understand what these spectra actually mean. So what Natalia and Frederick observed a few years ago is that I guess in this audience you're all familiar with this kind of diagram. So that's like the local effective Hamiltonian you have to solve in a DMRG step. And here we're in a finite volume, finite system calculation. So we have an extended system. This is the MPO here in the middle of the Hamiltonian. And these are the tensors of the bra and the ket of your state. And so the effective Hamiltonian is this local object. You calculate its ground state given this environment. And then from this you derive the new kind of tensor for the next iteration. But something which is kind of interesting in that paper is that they actually looked at the spectrum of this local Hamiltonian. As I said, usually one just calculates the ground state, takes the eigenvector and goes on. But actually it turns out that the spectrum of that object itself is interesting. And so what they observed is that as a function of iteration, there is actually a meaningful spectrum if you stop in the middle of a system, so like a symmetric situation like this. There's actually an interesting spectrum here in the middle, which is kind of converged up to some level, depends on the bond dimension, but the lower part is actually quite nicely converged, and actually this local spectrum is actually the spectrum of a boundary CFT. So it's kind of universal up to also a sound velocity, and then kind of these plots on the right from their paper show that the low energy spectrum, I mean, according to which boundary conditions there are and which theory there is a certain characteristic structure of the energy spectrum with certain relative spacing, and they all collapse as 1 over L, as you expect from a CFT. And basically knowing what the scaling dimensions of the fields are, because you know the CFT from the slope, you can actually then infer the speed of light that way. And so like these are two interesting aspects. One is that this local DMRG spectrum for kind of more than 20 years has been overlooked, that it actually has interesting structure. And second, it's actually useful to extract the speed of light with some precision. Yes?
But Andreas, is it fair to say that that has nothing to do with the DMRG? That's the spectrum of the Hamiltonian that you are putting on a finite system?
Yeah, but I think there's a bit of emergence here in the sense that I think they also in that paper, if the Hamiltonian is not critical, then actually the local spectrum here is not like one-to-one the many-body spectrum of the extended system. Right. So there is something that you have to work kind of in a regime where you're in the finite size regime of a CFT, where you're kind of regulated by the IR cutoff of the finite system. You have like enough bond dimensions so that the spectrum starts to see the entire system. And
that's fine, but that's the point, that you have to work with bond dimension large enough that this spectrum that you're seeing through the MRG is actually the spectrum of the lattice Hamiltonian that you have. I'm just saying it's nice, it's a tensor network conference, so tensor networks are cool, but this is a property of the Hamiltonian of the lattice that you are trying to understand.
Yeah, but I think the part which I kind of agree. I mean, I think if you look at it in hindsight, it looks obvious. But still, I think there's the point that if you do that for a gapped system, you do the same thing. You're not recovering like the extensiveness. I think because the effective Hamiltonian is built in the environment of the way.
So you would not use the MRG to see the Hamiltonian on the whole system. Yeah. In that case, all I'm saying is that this spectrum that we're seeing here, you will find it if you look at the low energy excitations. You could use exact diagonalization, right? And you would see that spectrum.
Yeah.
Okay. So it's nice that it appears in the MRG, but that's not the DMRG property, right? It's the spectrum of the original Hamiltonian.
You're right. It's that. But it's kind of, I find it interesting that at least in some regime, somehow the ground state, like the basis, the DMRG basis you're building up in your environment is then actually tailored to recover this on the entire system. I think this is kind of non-obvious, or
it's not obvious. I agree. Okay. Yeah. Okay. Thanks.
Okay. And also I found this kind of work interesting because at the time, it was actually not known if you do the similar thing now for an infinite MPS, so where you're pretending to solve for an infinite system, which is infinitely long, and then the only regulator is kind of the finite bond dimension. The question, what do you get there? Because you cannot get the complete continuous spectrum of a CFT on an infinite system. The spectrum would be dense, continuous, and so you can't see anything. So there is something induced by the finite bond dimension. And so now what we observed, which is kind of what I think is a cool result, is that we were motivated at least initially to understand kind of the corresponding kind of a local effective Hamiltonian spectrum. So that's this. You see there's a contracted left and right boundary. Here there are two kind of MPO operators of your Hamiltonian. So that's like one object. And then what we actually observed is another object which is famous, which is actually the transfer matrix across a unit cell of your IMPS setup. The two spectra are actually identical. And what is kind of curious is that, at least currently, I think all of us involved in this work, we don't understand the structure of what we observe. You see, so in the 1D case I just showed you for finite system, there the structure of the energy spectrum you see is the finite volume CFT, so that's a definite prediction. That's what you observe. So here we have to admit that we don't understand why the levels are what they are, like what is their relative thing. But what is interesting is, nevertheless, is that the local Hamiltonian spectrum and the log of the eigenvalues of the transfer matrix are actually identical. And so how do you see that in this plot? Is that these are different models. So this is the Ising model, 3-state pots, and this is a spin 1/2 Heisenberg chain for some moderately large bond dimension. And so we optimize for the ground state, and then we do this analysis of the local Hamiltonian spectrum of the transfer matrix spectrum, and one is circles are the energy spectra, and the crosses are the kind of the spectrum of inverse correlation length. And the only thing, so one thing is just like there's a common delta factor, but that's just for a global normalization for both of them. But then if you actually use the exact velocity, because all these three models have exactly known speed of light, then actually these two spectra, the crosses and the circles, match perfectly. And so I think that's an interesting observation. And then actually based on some path integral kind of a picture, Lawrence and Frank kind of came up with at least in a kind of in the Euclidean situation, kind of that the two objects, like the Hamiltonian spectrum, which is kind of the log of the temporal transfer matrix, and the kind of the transfer matrix spectrum, or the log of it in the spatial direction, should be the same. And so in the continuous time limit, there is also kind of some correspondence. That's also what Luca and his collaborators saw in a different context a while ago. And so that's like one part of the story, is that the two spectra, which kind of the structure of which we don't understand, but they are kind of identical up to a factor. And so then we thought, let's see whether we can turn that into a useful method to actually measure the speed of light. So we calculate for a given Hamiltonian the two spectra, and we find what is kind of the scale factor which matches them, and that's how we can extract the speed of light. And so now we show an application. So first we do some kind of reference or some checking by doing the series of the Q-state Potts model. So Q equals 2 is kind of a synonym for the Ising model. Then Q equals 3 and 4 are still have a CFT at their critical point. And so here you can see some actual numbers. And so for the Ising model, using these procedures of actually like kind of checking what is the scale factor which relates the subleading eigenvalue of the transfer matrix with the subleading kind of the first gap in the local Hamiltonian spectrum, we can actually reproduce the velocity, the speed of light up to almost five digits. And it's also something like 4 digits or so for the 3-state Potts model, and about 3 to 4 for the spin 1/2 Heisenberg model, and that's actually quite accurate. I think there are no comparable results using tensor networks, and there also was a recent work using some kind of RG Monte Carlo type approach by Roberto Carr and his collaborator, and I think these results here are way more accurate. And then as an application here in the spin business, what we did is now we can actually measure the speed of light or the spin wave velocity for the half-integer Heisenberg chain. So some of you might know that there is or was the Haldane conjecture that like integer spin chains have a gap, but half-integer spin chains have no gap, and they flow to a C=1 CFT in the infrared. And so with kind of a bare spin wave theory, you have some understanding that the spin wave velocity should like linearly increase. That's fine, but there's also kind of a more refined prediction that actually once you subtract off this 2s, disproportionate to s, there's actually like a remnant a contribution to the speed of light, so some additional stiffening. And since we now have kind of quite accurate results for this speed of lights, we can actually check whether as we crank up s, and we go up to 7.5, we can actually see that we're getting close to this expected value, which is supposed to become exact at large s. So I think that's an interesting application of things which were never calculated. One was never able to calculate that to high precision, and I think we made one step forward in that direction.
Question about that. The method you use to get the speed of light here, is it just to demand that the spectra are equal in the previous slide? Is that
yes?
Okay, so you just say that for them to be equal, there's a scaling, and that's actually the method to explain.
Yeah, exactly. Yeah.
Okay, thanks.
So if you approach a new system, I think here this is a plot. As you can see, there are like on the order of 10 or several tens of eigenstates in both kind of spectra we calculate. This is just to convince ourselves that it's kind of conformal. The two spectra are the same, and once we're convinced of that, we can basically take any pair of corresponding state and extract its velocity. Turns out that the lowest one is usually the most accurate. That's the one we kind of quote as the number. Yes?
So you mentioned that you have some physical understanding of why you expect the two to be the same. Could you say a few more words about that?
Lawrence, do you want to say something about that? No, but the idea here is kind of, okay, perhaps you can't see but here if you like trotterize the time evolution of kind of a path integral representation, it's some imaginary time evolution, then in some limits you can convince yourself that the transfer matrix in space and the transfer matrix in time are the same up to up to the scale factor. But one has to say, you see, you need some underlying picture that there's a CFT, that there is kind of Euclidean invariance or something like that in the first place, and then once you kind of wrap that into a tensor network, that's what you observe. But again, as I insisted, at least with some questions on the 1D case, I think this is an emergent quantity. Already on the very naive level, you see that the object, which is the Hamiltonian spectrum, and the transfer matrix are not identical objects. They don't even have the same bond kind of dimension. So at some point, these spectra will deviate from each other. This is not an identity on the MPS level. It's an emergent property. If your MPS is somehow optimized to describe a CFT, then that's what we get out. Okay, and then we had another application where we look into kind of itinerant or at least partial itinerant system. So we looked into a Hubbard chain and a Hubbard ladder, a two-leg ladder. And so the Hubbard chain, for example, is an attractive U Hubbard chain. At that point, it has a spin gap, but there's a gapless charge mode which is there. And then we can measure that model is integrable, and then one can actually get, for example, the speed of here is the speed of light. We can get the speed of light from a comparison with the Bethe-Ansatz case. But this is just to show that here for the Hubbard chain, it's a system which has more degrees of freedom than just like the spin models we looked at. And so even there's a gap in the charge sector, in the spin sector, then the charge sector still shows this emergent behavior, and we're quite close to the Bethe-Ansatz result. And then the second problem is a bit more non-trivial. It's a two-leg Hubbard ladder at finite doping. There it's also expected that this is a Luther-Emery liquid, which means it has a spin gap, and there's a gapless charge mode, which should be responsible for a 1D analog of superconductivity. And so using kind of this technology, it's now possible to extract the speed of light. So that's these curves here on this plot as a function of the filling. One can get quite accurate results for the velocity, and then one can also using established technique, measure the compressibility. And for those of you who have some prior exposure to Luttinger liquid theory, if you know the velocity and the compressibility, you can actually infer the Luttinger liquid exponent, and then that's done in this inset here. And so you can study the Luttinger liquid exponent, which tells you whether the system is more prone to charge density wave fluctuations or to superconductivity. You can study that here in the density regime, and also close to the Mott insulator at filling 1, where there are some predictions, at least our data seem to converge. And there are also some 2 other data points from work by Dolphy and others, and there they did kind of fitting of correlation functions in real space, but we believe that this is kind of less accurate than what we do, because the correlation length, the real space fitting is much more impacted by finite bond dimension effects and so on than kind of this matching of the spectra which we do. Okay. So I think that would conclude the speed of light part. Are there questions on this? Yes?
Is it correct to say that the speed of light is you just look at the CFT, right? It has a cone structure.
Yes.
Look at the stress tensor, which has scaling dimension 2 and spin 2. And that's you would like to fix the speed of light such that this is a line. So you can do that on a circle as well.
Yeah.
Right. So I think what you're saying is that you understood how to do that with the scaling of one dimension to the third power, which allows you to reach much more precision. But I mean, there were previous methods on the circle with periodic boundary, periodic MPS, where
so
this could be done.
You were part of those, I guess.
Well, I don't remember. No, all I'm saying is that what's really great is that you managed to simplify, to just use one dimension to the third power methods, which allow you to. That's the essence.
Yeah, I think I'm excited about results for 2 reasons. So I think one is what you just said. I think it's of practical value. It allows you in a cheaper way to get, in case you're interested by this quantity, it's non-universal, but say in a condensed matter or a kind of cold atomic gases, sometimes we're interested in those numbers just because they tell us like what temperature, and so on. So I think it's interesting. And the other thing is also that at least because I was just kind of fascinated by this. I think there are 2 spectra which at least currently we don't understand, but they're actually the same. And I mean, it's kind of my personal fascinations in doing numerics. Every now and then I stumble over kind of things which have to do with field theories, and somehow you do kind of naively linear algebra in some more or less complicated way, and suddenly you get the glimpse of field theory structures or emergent kind of things which are the same, even though microscopic. This is fascinating. So I don't know. Yes?
How difficult is it to introduce next nearest neighbor interactions? Because if they're frustrating, you can really slow down the speed of light, or maybe is this something?
But I mean, technically, I mean, kind of as long as you have a Hamiltonian which you can describe with an MPO, and frustration or further neighbor is not a problem, you can do that. No, there's no assumption on the structure of the Hamiltonian. I mean, you have to write it as an MPO, but you can do that with further neighbors. There's no problem. Okay, there's another question.
So, is there any reason that you looked at this 2-body effective Hamiltonian? Because you should be able to get just the same results with the effective Hamiltonian of C, based on this argument.
On what? What's on?
Like just like there's an effective Hamiltonian for the C, right, which is a chi-squared eigenvalue problem.
So you can take out one. You want to take out both? You mean?
I want to take out both.
Yeah.
And you should be.
We have not checked. I think my student Alex, he did also a thing with just 1 instead of 2. But I think with none we have not tried. But you're right. I mean, in the end, in the end, there's a lot already of information basically in the whole contracted MPO with the boundary. I mean, with the But I haven't.
It's not the spectrum of C, it's the spectrum of the C eigenvalue problem.
Yes. The effective Hamiltonian on C, right?
Yes.
I say that this is related to a corner transformatic spectrum, so to an entangled spectrum that we understand the structure. Whether this transformatic spectrum here, we don't understand the structure.
Really?
When you mix the scale, physical and virtual, we don't understand. When we only have the virtual, typically it well represented by some kind of
I think you're referring to the spectrum of C itself, because it's not
of the environment. No?
But this,
basically this thing is where you just leave out small h's.
Yeah.
You still have the actual line with the MPO.
Yeah, exactly. The whole MPO is actually contracted apart from the central stuff. I think even if you leave it out, it's.
You wouldn't have physical legs, but the Hamiltonian is still in the equation.
But I think that's relevant. So what is relevant if you talk to the ultraviolet scale or not? I think. So in principle, your body structure scale is somehow infrared. And so if you don't have physical legs in there.
But I mean, the easiest is we can check it in actual calculation. So perhaps we can discuss this later. Okay.
So just to say, like, based on your argument, it should be the same spectrum, right? So it cannot be that you can explain this the just eigenvalue problem for C, that you understand this spectrum completely, but not this spectrum, because they should be the same based on this argument.
Yeah.
Also, just
but I'm also inclined to believe your suggestion. It might actually be that if we completely take this out, then it's it should actually.
And it should even be like if you say, like, you were saying, like, the two spectra should be kind of the same, but it's clear that they cannot be the same because they're not even the same bond dimension.
Yeah. Then that's a way to circumvent that.
Indeed. So
Yeah.
maybe this will work slightly better.
Okay. Yeah. Thanks for the suggestion. I mean, from a pragmatic point of view, it's just that, I mean, in kind of in existing IMPS implementation, something like that actually pops up. So in that sense, like, the change is really minimal. I mean, okay, we can discuss how much of a thing it is, but it's also something I just I forgot to mention. But this is kind of not a new algorithm in the sense that you have to, like, invest a lot of kind of a new algorithm to do that. You basically just have to, in one step, instead of just getting the ground state when you do a DMRG step, say at the end or something in an evaluation run, you somehow just compute the low-lying spectrum of your effective Hamiltonian, and then you're ready to go and do this analysis. So there's not a large overhead in somehow implementing something new to get access to this information. Okay, and so now I would like to switch to the next topic, and so. This is, so I will briefly talk about finite entanglement scaling. I mean, Luca already gave us an introduction yesterday, and I will point out that even though this works quite well, I think there's still some room for kind of systematic improvement, and we try to circumvent or to find a way to do that, at least in some simple cases. And so this is kind of a 1 or 2 slide summary of how this finite entanglement scaling works. So first of all, we are working again in the infinite system MPS version. So we're not talking about finite system, but infinite system. And then since critical system cannot be described by a finite bond dimension infinitely accurately, there is kind of some effect of that. And it has been observed by Luca and also by Frank and company that kind of there's an empirical or almost or semi-empirical relation between the induced correlation length in your MPS and the bond dimension in your system, and with the exponent kappa, and from some kind of entanglement spectrum scaling arguments by Lefebvre and Calabrese, you can kind of come up with this exponent kappa, which depends only on the central charge, and so somehow this exponent here will change if your central charge of the theory changes, but you have a power law relation between the correlation length and the bond dimension you put into your system. And then as it's known, once you have a finite correlation length, this also regulates or cuts off your entanglement entropy, and you have these entanglement scaling with either the correlation length, then it's just C over 6, or if you replace xi with d to the kappa, then you can pull out kappa, and then you get this scaling with the log of d. And so this is all beautiful, and I think it's also used a lot by the community to actually estimate central charge in the IMPS framework. And in many cases, it's quite okay. But this is a bit of provocative slides where I would like to point out that at least if you want to do high precision, there is some kind of underlying kind of subleading effects or discreteness effect of bond dimension, which are not accounted for by this kind of a continuous formula. And so depending on how precise you want to be, there is some kind of challenge. And so what I think what one typically does now is actually plot here the entanglement entropy on the vertical scale. And here there are two data sets. So black is I plot log D on the horizontal axis, and red is I plot kind of as a function of the logarithm of the transfer matrix with the correlation length. And so you get these two different lines. And so this is the critical Ising model. And so then you have these data points. And now we calculate a lot of different bond dimensions. It might be that even we took them one by one up to of the order of 64 or so. And so usually what one does is to actually fit this data to a straight line. And from the slope, you can infer kappa, C, or C itself. But what I want to point out, and that's the provocative part, for example, if you just look at finite differences between adjacent points, you can see, especially for the log D part, I mean, the scattering is huge. I mean, once you fit over the entire data range, you get reasonably accurate results on the order of, say, % level or so. That's, of course, okay for many applications. But also the log psi still has kind of noise if you kind of put it to the extreme by looking at adjacent point. And that somehow tells you that this is not yet a theory which can be or is able to be systematically refined. And if you want to just somehow now know a central charge to much more precision, I think there's some current limitation the way it is done in this finite entanglement scaling, just because we don't understand kind of beyond the leading order formula what is like the impact of the discrete choice of bond dimensions on correlation length or the entropy. And so what we, sorry, yes?
Sorry. Are these orthogonal distances to the line? Or measured, in the y direction?
Sorry, say again. What's the question?
Like these dots, right? They're supposed to be distances to.
These?
Yes.
But these are just finite differences. Like I infer kind of the instantaneous slope.
So you don't expect these to be just bigger because the slope is bigger?
No, the slope is kind of constant, no?
No, but the slope of the black is bigger than the slope of the red.
Yeah, but that's reflected by this fact, no? So these, I mean, here there are two lines. One is the exact one, and the other one is the slope obtained by the fit over the entire data range. And the same is true here. So I think actually the two differences, I mean, they're quite precise as such. But this is just if I do the finite difference between adjacent point. I think this is really amplifying the effect that even the relative change between points at large bond dimension is actually substantial. That's, I think, what this plot shows. So it's not that somehow these oscillations become smaller at large bond dimension. They actually are still are not going away.
Wouldn't you expect if it's like Gaussianly distributed in orthogonal distance from the straight line, and then you, let's say you just make some points.
I mean, you can go forward and come up with a theory what dictates this fluctuation. That would be welcome, but currently there's no such understanding. I'm just pointing out this is not understood.
I'm just trying to see whether this discrepancy might come from just the difference in slope. Like if really the distances, orthogonal distance to the line was just the same, but you would make this plot, would you, just because the slope is different, would it look like there's a difference? That's the thing that I'm wondering.
Yeah, I don't know the answer to that question. Yes.
Look at only the red data. It's just pointing out that there's spread in it.
I know, but I'm saying, like, I think if the slope increases, then there would be more spread. So
is it a standard deviation around the curve,
so
or standard
this
deviation?
may just be an overly technical point for the length of this talk, so we should go on to the other slides. So.
Yes. Excuse
Okay, but I mean, as I said, it's provocative. I'm not saying that these methods have a lot of practical value. I think one should continue to work with them. But I'm just saying, I think that there is something which does not just make them infinitely more precise if you push bond dimension. Usually we think about that. Things just get better. I think these do not necessarily get better with bond dimension. That's my main point. And I think that's currently correct, or at least a correct observation in my opinion. Okay, and so now what we do next is kind of the idea we bring in. I mean, the idea itself is not new, but it's perhaps new in this particular context. So you see there are different ways to kind of regulate the CFT or to kind of go away from it. So we now know from this prior work that once you have a finite bond dimension, correlation length is finite because of that. And then you can analyze the data, even though all the details are not understood. But another kind of more obvious way to kind of gap out the CFT is to actually couple to a relevant perturbation. So many CFTs actually have relevant perturbations, and often in a kind of a context we understand what kind of lattice operator we can write down to actually kind of couple to some of these relevant fields. Usually it's dictated by symmetries or so of the problem. But then what generically happens, and that's basically the field of conformal perturbation theory, is that kind of the vicinity of a CFT, once you couple with lambda, is kind of the coupling to a relevant perturbation. And this is just like written kind of in field theory language, so it's a spatial integral of some operator. But once we switch on a non-zero lambda and phi is a relevant field, kind of we flow to strong coupling, so away from a CFT, but we usually open a gap. And so there's a mass gap and correspondingly a finite correlation length. So this is all well known. And this is kind of the usual RG relation between the correlation length I, which you now kind of generate by a finite coupling lambda, and kind of the power law relation actually has to do with the scaling dimension of the field to which you couple. That's this delta phi, because phi here is the perturbation, the relevant field. And so we kind of gap out the system and use a finite correlation length. And therefore, that's also like a result known from Calabrese-Cardi and so on. Is kind of this result is that in the vicinity of a CFT, when you gap out, then kind of the entanglement entropy is now dictated by the finite correlation length, which here depends on the relevant perturbation and not on the bond dimension. And then you have this relation. So again, this is not new, but then as such. But then what we do, I think, which is not. I'm not aware this has been done before, is now, you see, we take this relation, kind of it's obvious, but now we invert it. So we basically mean that we express the correlation length via this formula, basically as the exponential of some difference in entanglement entropy, and then there's also this factor C/6 appearing. And so what we're now suggesting is that we perturb away from a CFT. So there's this coupling lambda, which dictates which value we choose. But then we actually want to analyze things now not as a function of correlation length, but actually as a function of entropy. And so that has a little bit of a flavor of, say, entanglement renormalization, which also people have been advocating. It's not exactly that, but I think there's a flavor to it. And so if you see, usually you have a relation, say that the induced expectation value of the field phi scales as a power law, like as delta phi with lambda, but since now, or as a correlation length, but since we replace the correlation length with this expression, so basically the exponent enters here as a prefactor in front of the entropy, and then you can also kind of have this relation between lambda and the entropy, and then you see this RG exponent pops up again. And also another thing we like is actually the excess energy. You could argue that at the CFT you have like your reference of the energy, and then if you perturb your wave function away from the CFT and you ask what is its variational energy still at the CFT, then because of the variational principle it has to be positive, and so the excess energy is actually also controlled by the correlation length. And since the energy, as Guifrey said, is that it's related to the stress energy tensor with the scaling dimension 2 for these CFTs. And so here the scaling dimension is not known, but it's 2, and that's why there is now this 12/C. So these are kind of simple relations. And if you make them a bit more precise, so in the end, what is the point is that we do simulations for different values of lambda. We can then measure kind of excess energies or also local magnetizations, or here it's deviations of magnetizations. And the idea is that now that if we take the log of these measurements and we take the numerical derivative with respect to entropy, we actually get simple expressions. For example, if we do excess energy, take the log of it, take the derivative with respect to the entropy, we get the 12/C. And so the idea is by basically calculating numerical derivatives with respect to the entropy, we get the proxy or an estimate for the central charge. And here we get then, once we know then the estimate for the central charge, we can get estimate for the scaling dimension. And so on. And so that's kind of the program. What we do, we perturb away, we do a run with different values of lambda, and then we take derivatives with respect to the entropy, which we also measure, and then we get these estimates. So let's see how that works. And so as always, we start off with the Ising model. So this is the Hamiltonian, and we have two kind of different perturbations which are relevant. This is well known from the structure of the phase diagram of an Ising model. There is like a thermal axis in the absence of field. That's basically the thermal coupling, the epsilon field with scaling dimension 1. So that's responsible, for example, for the exponent nu. And then there's also the coupling to the order parameter, to the sigma field, and that has a scaling dimension 1/8. So if you couple to the local C magnetization in this Hamiltonian convention, that's actually coupling to sigma. And if we detune the transverse field from its critical value, then we're basically coupling to the epsilon field. So now I show a result for the first case where we couple to the longitudinal field. And so now what I'm showing is that, so it's Ising model, we're detuning with the longitudinal magnetic field, and these different points are different values of lambda, of this perturbation, and we lose like a logarithmic grid, which means like we reduce the value of lambda by a factor 2 from one point to the next, and so here lambda is very large. Basically, our spins are all pointing up, because that's what the effect of the longitudinal field, and then we reduce lambda more and more. And so this is just bond dimension 4, so it's ridiculously small. And here on the axis, I plot the entropy of the optimized MPS, bond dimension 4 for different values of lambda. And what I plot here is now this running exponent, this running central charge obtained by basically the log derivative of the excess energy with respect to the entropy. So that's the curve just for bond dimension 4. And then to see what the bond dimension does is that if we increase bond dimension chi to 8, it lies on top for large values of lambda, then it continues a bit further. And so if we do that to larger and larger values, so here on this plot, we have bond dimension up to 256. And so we get visually close to 1/2 as we expect. And so then you can do a more quantitative analysis. So again, here this is the same thing, but now we subtract 1/2. That's the expected central charge, and this plot basically shows you if you push the bond dimension quite hard, quite a lot, then using this running derivative, we can actually get a running estimate of the central charge of the Ising model, which is accurate to 10 to the -4, so quite a bit larger than the percent level we had before in the standard entanglement, finite entanglement scaling. Yes. No.
You just change the bond dimension and do the derivative with respect to the bond dimension of the entropy. Wasn't that the spread that you had around?
I don't think so, but okay. Yeah. And so this is the central charge, but then we can also do, for example, get the corresponding estimate for the scaling dimension of the sigma field, 1/8. Which is expected, and here you can also see it's getting very accurate, and I think here we are approaching something like 10 to the -8. That's also extremely accurate. And another thing is that also we can get, using the same perturbation scheme, so still with the longitudinal field, we can actually also get access to the scaling dimension of the thermal field, and that's the reason it has to do with the non-vanishing OPE coefficient, which means that if you perturb the Ising model with a longitudinal field, it automatically induces also a change in the thermal field, and so we can basically measure what is the sigma x. How does the sigma x expectation value change with respect to the value at criticality? And that change is also governed by a power law, and it's basically controlled by the scaling dimensions of the thermal field. So we know that one is 1, so we can also check. And so here you see the 10 to the -1, 3. So this is about 10 to the -4, I would say. And so we're getting on the order of 10 to the -4 for this. So here this is just it's an accurate proof of principle or demonstration that this works. One has to say that if one looks at MERA results or also these PUMPS results for MPS spectral methods on finite rings, I think these precisions are probably comparable in some cases, perhaps more accurate or less accurate we can discuss, but it's not setting entirely new records, but at least within IMPS, I think this is a quite nice application where actually regulating the CFT with a relevant perturbation and then analyze as a function of this the coupling gives quite nice results, and I think it's more it leads to higher precision than the standard scaling with finite bond dimension. I would say, at least for these cases here. Yes.
Have you thought about using automatic differentiation to take the derivatives?
No, we haven't. No, I think we're already working a bit long on this project, but I think when we started, that was not on the market, at least not in the tensor networks. But you're right, that's perhaps something we should also think about, or in a one. If someone is interested to put this into production, there are probably improvements like what you suggest to use AD to push that, yeah. Because it's true, I didn't mention it, but of course these are done using kind of a more or less naive finite difference formulas in entropy. So there's also a discretization error, which I don't. But I mean, it's not so dramatic because these derivatives anyway go down. So I think usually it's just like a prefactor. It's not somehow changing the orders of magnitude of the correction, but it's something which one should take into account as well. Okay. And this is kind of just a non-trivial application. So this is again kind of Heisenberg spin chain. So this Haldane conjecture which popped up in the first part as well. And so you see Haldane conjecture basically maps the physics of these spin chains. So it's Heisenberg spin chains with various values of S. And as I told you, for half integer S, you would expect that in the infrared, so at long distance, your chain goes to a C equals 1 CFT, whereas the integer spins actually go gapped. That's kind of the answer what happens in infrared, but actually in the UV, or as the at intermediate scales, actually the theory of the nonlinear sigma model would actually say that this system almost looks like two massless fields, so it actually has an effective central charge of 2 at intermediate scales. And only in the infrared, you either go to C equals 1 because you go to this Westomino-Witten theory, or you go gapped and then the central charge is kind of 0. And what I like is that here, kind of this is all visible in this plot. So what we do is, again, we calculate the running central charge by the same means, and we look at different spin chains. And now what we're doing is that the Heisenberg spin chain are actually one of the very relevant perturbations is to apply a staggered magnetic field, because they want to be almost antiferromagnetic. So if you actually have a staggered magnetic field, it gaps out immediately. And so that's basically the perturbation we do. Again, these different points are different values of the perturbation. And so now what is nice is that if we do that for spin 1/2, it's what you expect. It starts at 0, it overshoots slightly, but then it approaches C equals 1, as it should, because the Heisenberg spin 1/2 chain is known to have C equals 1/2. And then if you do spin 1, it rises the same thing, it overshoots, and then at some point it breaks down because spin 1 chain is gapped, as we all know. But then we can continue this game. So spin 3/2, actually it rises from 0, then it hovers somewhat above 2, and then it slowly drifts and crosses over to C equals 1. So I think that's a quite nice illustration that somehow in the UV or at intermediate scales you're almost at 2, and then you somehow, there's a crossover flow to C equals 1. And then you do spin 2. So spin 2 also joins, does the same as spin 3/2 for a while, and then it also overshoots and it breaks down because, again, it has a gap. And then the other ones which we can reach, so spin 5/2 and spin 3, they actually follow this thick dashed line, which is actually the spin wave theory. And that one goes indeed to this C equals 2 because it's effectively two massless bosons. And so that's kind of the intermediate scale prediction, and that's kind of this. I think you see this C equals 2 is also, you can call it asymptotic freedom in the nonlinear sigma model. And so that's something you can actually see through this analysis. And I think that's also a nice way to see these concepts at work. Like at intermediate scales, if you crank up S, the intermediate scale has C equals 2. And then the infrared, you either flow down to 1 or you go to a gap and C goes to 0. So you see this kind of Haldane conjecture at work, and kind of some result from the nonlinear sigma model pop up here. Okay, so I think I'm done with my time. I had a few questions. I would just like to advertise that some of these questions with relevant perturbation, we actually have a preprint out where we use that already to diagnose weakly first-order phase transition. I don't have time to explain that, but one of the results is, for example, that if you do this technology and applying, not using tensor network, but using QMC, we actually think that the JQ model on the square lattice is actually weakly first-order and not the deconfined critical point. And then I jump this 2D part. You can ask me in the break or read the paper if you want. And so, sorry, they would like to acknowledge the collaborator. So Alexander Eberharter was involved in both as the PhD student. He did most of the numerical work in those projects I presented. Michael Rader was the student who did the work on the IPEPs, which I couldn't tell you. And then Lawrence, who's also here, and Frank Verstrate, who I guess you all know, they were involved in the speed of light project I showed you in the beginning. And with this, I conclude with some plots and I stop here. Thank you.
Okay, let's just take like one question. So does someone have a question after Andreas' talk? We already had a few during the talk. Yes.
Why the entanglement scaling doesn't necessarily improve with bond dimension, but when you scale it with the entanglement entropy, the error is controlled. Like,
yeah, I mean, the two things are different is that the source of regulating make entanglement entropy finite is not the same in the two schemes. One, it's really like a relevant perturbation, and then on kind of on more conventional physical grounds, you expect the correlation length to be finite, and then you can work with a bond dimension which is large enough so that it's not, the bond truncation effects do not show up. I think the main reason is that we have like a leading order or understanding of what is the impact of a finite bond dimension on an infinite MPS, but we don't have a theory which can be systematically refined. So I think it's correct. It's like a good effective theory, but we don't know what additional terms or corrections we have to take into account to make that theory or that description more accurate. I think we're lacking the next step or the next orders in whatever that expansion might be.
thank you.